All right, we're going to get started since it's noon. We might have some more people trickle in. That's general practice for our brown bag sessions. But I want to thank Dr. Dewookar for coming out and bringing his team with him. Ian Anderson, it looks like he's going to do most of the presenting. Lalita Oka, Dylan Walsh, and George McCain, Mark Suozzo, and Bradford Berry all work on this project in various stages, I'm sure, because the ones on the bottom actually graduated. And as you probably know from the invite, it's concerning the pervious pavement lot that's literally right out here between us and the Parking and Transportation Office. So with that, I'll let Ann take it away.
Great. Thanks, everyone.
Oh, I'm sorry, one more thing. If you didn't sign in, have a sign-in sheet. Anybody not signed in? We'll pass it around. Okay, great. And now take it away. Sorry.
Okay, thanks, everyone. I don't know how that works, so every once in a while it's going to beep if somebody on their computer does something. This is our talk on pervious concrete. It's going to cover the work we've done through various research projects, as well as some of our latest stuff involving the parking lot that we got an opportunity to take part in. So for those who don't know, pervious concrete or porous concrete or porous pavements, pervious pavements, it's a method of allowing the natural water that would rain to flow through and infiltrate down into the subsoil or be contained in a storage area. Provides the same hard, clean surface as we're used to with asphalt and concrete, but it has that natural infiltration capacity. So we reduce runoff, we reduce secondary contamination from the vehicle fluids that a lot of times fall in the parking lots and stuff like that. So here's a couple of examples. This is a section taken out of a parking lot. You can see it's about 5 inches of concrete with a large void space to allow the water to flow through, like in that demonstration there. And then below it you have some aggregates and some storage capacity. So to start off with the project that most of our research has developed from, this is the Randolph Park and Ride in Randolph, Vermont. The Department of Transportation got a grant to try this new type of pervious pavement, so they went with porous concrete. You can see it's a two-staged lot, entirely made of porous concrete. And then a couple of other sites around Vermont. We have Heritage Flight in South Burlington. The entire lot's made of pervious concrete. Been there for a couple of years now, having some pretty good results from that one. And the third one would be the College Street parking lot down by the Echo Center. I know a lot of people have probably been down there and haven't even noticed it yet. But in the parking lot, it's a little easier. So in the parking section, the area beneath the cars is pervious concrete. The area outside of that is asphalt. So the theory is the water will run from the asphalt into the concrete, infiltrate down into the soil, and in this case, it's collected and discharged into the stormwater system. So to move on to some of the work that we've conducted through our various studies, we've been working on mixed design evaluation, so trying to improve the mixed design to adapt our northern climate. Pervious concrete has been used throughout the United States with varying success in different areas, and we've had some trouble because of our cold, harsh winters, freezing and thawing, the use of road salts. So our work has been to find a mixed design that will work when put out into the field in everyday use. We've worked on standardizing some laboratory testing procedures with compressive strength, hydraulic conductivity, getting the properties of the concrete so we can make repeatable batches. So those include strength, infiltration, and the durability of the concrete. We've also worked on field monitoring, measuring the infiltration capacity in the field, seeing the improvements, decay, working on cleaning to try and rehabilitate some of that infiltration, and specifically winter exposure, so road salts, freezing and thawing. So here's a little bit of background on the compressive strength, sort of the core value of strength that we measure for pervious concrete. As you know, it's concrete, so it won't be very low in tension, so we're mainly relying on the compressive strength. to take the load from the vehicles or anything that's placed on the surface. We have a pretty general positive trend between the density of the pervious concrete with the compressive strength. So the heavier, the stronger you make the concrete, the better, or the heavier and more robust you make the concrete, the better compressive strength you'll get. And we've done work with some of the testing methods so that when you go into the lab and you're testing samples over and over again, you get consistent, repeatable results, because unfortunately for pervious concrete, these test methods that you would use, ASTMs for conventional concrete, sometimes don't apply directly. So we've been working on developing some of our own methods.
Question for you on that
Yep.
chart. The different studies that were used in generating the plot, are those with differing batches, or is that using the same batch of or same mix of material?
For most of them, I can't speak directly to all of the literature that's cited because I haven't read them specifically, but these would be for a batch of concrete. So yeah, it would be the same mix, but it might have been two separate batches. One, you would add a lot of compaction energy to get a greater density and continue moving your samples up that trend. So one group of concrete might have been made a little bit lighter to have higher infiltration capacity, and then you can take that same ingredients, compact it heavier, increase the density. So the opposite result for the...
Can I ask a question?
Sure.
Just on the last slide again. For your study, does yours have a statistically significant trend in it?
Yeah, this plot was taken from a different study than... So our study, the blue ones there, are pervious concrete including fly ash. And so there's a little bit more intricacy in the different mixes that were all lumped into that. So
Oh, okay.
this is sort of just a general trend with any pervious concrete you make. You'll see a positive increase in compressive strength.
Gotcha, thanks.
Okay. So the inverse of the compressive strength can be seen in the hydraulic conductivity. That's the amount of water that can be passed through. So with a greater density, in order to get that greater strength, you're closing the voids and creating more contact between individual aggregates. And in doing that, you're reducing the volume of water that can be moved through. So we see a pretty uniformly negative trend amongst all mixes that we've tried, and just put on a general line there for you. So hydraulic conductivity really depends on the pore size, and the connectivity, which comes into play with different methods of construction and compaction. If you use the wrong type of compaction, you'll be creating layers of dense concrete on top of each other, and you'll lose that connectivity for the water to flow through. So some of the tests we've done for compressive strength have dealt with the sample size in the laboratory, whether having a height to diameter ratio of 2:1, which is recommended, and testing those effects when you reduce the height to diameter ratios to 1.5 and 1, and also the end capping conditions. So we have a rubber pad inside of a metal cap, as well as sulfur capping. Testing to see which one gives us a better statistical result to see which should be used when finding laboratory values for the compressive strength.
Can I ask you a question? Do you install them as those little cylinders?
No, so those
Those
are what are made in the laboratory in order for us to test mixed
But
designs.
you install them as blocks or
Yep.
continuous
Yes.
material?
So some of the other standardization work that we've done is for the infiltration and hydraulic conductivity. On the bottom, you'll see our laboratory hydraulic conductivity testing apparatus. So the sample is inserted between those two rubber hose clamps and sealed on the sides so that we have only vertical flow. The water is poured in the upstream, and the falling head is measured as it passes 2 points to find the hydraulic conductivity. So that's sort of our laboratory hydraulic conductivity value. And then, so when you're in the field, you pour the concrete and you have no real way of knowing the hydraulic conductivity. You can't take a sample of it without drilling into the concrete, which most people don't like. So we tested 3 different methods. The field infiltrometer developed here at UVM is a simple falling head apparatus measuring the amount of water that goes right down into a 4-inch opening, as well as the single ring and double ring, which were modified from soil testing. Single ring is the same concept, measuring the volume of water that goes in over a certain time. The double ring creates a column of water around the internal ring that we're testing, so it creates more of that vertical flow that you would see in the field infiltrometer. And so some long-term field monitoring study was done to use the laboratory field, or the field infiltrometer was used to measure the performance of the College Street and Heritage parking lots over time, measuring the infiltration values as they go and monitor clogging. And then a separate test was done to go and try cleaning those sites, having a street sweeper come out or using a pressure washer or hand vacuum to see if we can rehabilitate some of the infiltration capacity.
So what is the rainfall or what is the typical infiltration rate that will be needed to accommodate, let's say, 100-year storm or something, just to put things in perspective?
Sure. Well, as you can see, these would be magnitudes greater than any storm you would see if you had a direct rainfall on top of it. I mean, this is 10 inches per hour, and all of these are accommodating that perfectly well. If we had 10 inches per hour, we'd be standing in water. So they have much higher infiltration capacities because we've been able to keep these lots clean. What we're looking for is a general trend so that if it's in a situation where it becomes clogged, we would try measuring that. And so.
And at this lot, we also tried vacuuming and bringing a vacuum truck and seeing how much was the improvement and those kinds of things.
This would inform how much sort of ratio of non-pervious area to pervious area you could have to accommodate sort of runoff from one to the other, I would imagine.
Yeah, that as well. Similar to the parking lot outside. So the work that I did specifically has to do with the freeze-thaw durability of pervious concrete. The concrete, which is made up of aggregates covered in a thin layer of cement, gets compressed together so that the contact points take place between the cement. So you have individual aggregates completely coated in cement that are then bonded together. And the voids is where the water will infiltrate. And so the two issues with that is if the pervious concrete is totally saturated, whether the whole system has been flooded or there's clogging, the expansion of that water that's inside the voids when frozen will act to push the aggregates apart and break the cement as water increases in volume as it freezes. And the second issue is more on a microscopic scale. Cement is a porous material down, at very small ranges. And so water, which gets inside of that cement paste and in between the aggregate and the cement, when frozen, see there would be a small boundary layer of water. When frozen would cause the cement to flake off, which we call scaling. And so that process causes the structural integrity of the individual cement covered aggregates to lose its bond and strength. And this method of damage is especially important when you're dealing with road salts, which would magnify any scaling on the concrete to a much worse effect. And so the test that I conducted used varying levels of salt concentration on the same batches of pervious concrete. So the ASTM standard for these tests is to place them saturated in water in a freezer and it fluctuates freezing and thawing 7 times a day rapidly out to 300 days. I used a different test method because I wanted to try and mimic field conditions. So these are frozen for 16 hours and thawed for 8 hours a day. So it's 1 cycle per day. And the freezing and thawing happens over a longer period rather than flash freezing and thawing using heaters. And these samples were submerged in salt water, removed and allowed to air dry in the freezer. So it's freezing in a drained state, similar to what you would see in the field. So the idea behind it is, in a field, it will rain, the salt that's on the road or snow will melt, run through, and freeze, rather than being frozen in a saturated state, which you wouldn't see in a functioning parking lot.
For those scaling effects, you have water getting right in the cement between the aggregate.
Yep.
I guess if you actually have a dry condition, is there, how long does it take? I mean, is there like a lag between, all the interstitial phases draining and then the cement aggregate water? Is that lag by a certain period of time, or is that drain pretty much at the same time as it would for large scale effects?
The concrete actually contains water in the mix,
from
there's
the natural water.
Yeah, there's water inside the aggregates already. The damage occurs as that water is drawn back and forth across the cement membrane, and so if it's not allowed to dry properly, and if there's salt, especially because the salt raises the saturation, so any increase in saturation will result in damage, and the salt is especially damaging because salt will hold that saturation longer. So if you allowed it to dry or put it in an oven and then froze it, you wouldn't see much damage. But if you're placing it in water and immediately freezing it, it hasn't had time to then dry out. And so the salt, we think, increases that damage. So you'll see with plain water, which will be the circles here, you see very little damage, less than 5% of the total mass. And with our higher salt concentrations, 4 and 8%, you see much more damage. Also interesting is the 12% salt, which you would think, you have 2%, 4%, 8%, you'd think the damage would increase then at 12%. But what we've seen is that in this case, with the temperatures that we were freezing it, the 12% sample wasn't reaching its freezing point because the salt concentration was higher. So with a high enough salt concentration, you could avoid any freezing. But if I did take those individual samples and freeze them to a temperature low enough, I think you would see even worse damage.
So what temperature were you freezing to?
These were at negative 20 degrees Celsius. Yeah, not Fahrenheit. Negative 20 degrees Celsius, and then allowed to thaw for 8 more hours. So with higher salt concentrations, you raise the saturation, and the damage that occurred in the samples occurred in the core at the bottom. So if you took a sample, saturated it, and placed it to dry, the drying front would go from top to bottom and from the outside in. So the bottom center of the samples is where we saw the most damage, correlating to where the greatest saturation would be. And with these drain samples, which is contradictory to the ASTM method, water alone causes very little damage. In the ASTM method, they're placed in water and freeze thaw rapidly, and you see lots of damage. So that was sort of my argument as to we need a better test method. The conventional concrete testing method doesn't work properly. So the current study is using that same freeze thaw process, trying various mix designs. We have our water control, so those weren't in salt, and then a base mix with salt, and then changing some of the properties of the cement using slag, cured at 7 days, 30 days, fly ash, cured at 30 days, and slag and silica fume. So to explain what some of those are, slag and fly ash are cementous alternatives. They're byproducts of the coal combustion process. So they have similar properties as cement, where the addition of water and an ample amount of curing will turn them into a hard substance like cement. We have been incorporating them into the concrete to increase the durability of the cement paste, to make it a little bit more robust, and to try and decrease the cement's permeability to see if we can block the water from moving back and forth across that cement. And then the various curing times are to see if there's an effect with these new cementous alternatives. There's a different amount of curing that's needed as opposed to our standard 28 days for cement that we've been using in the lab. And then slag and silica fume is one of the products that's being incorporated. It's a blend of the two to, again, increase the durability and robustness of the cement base. So we've seen some immediate mass loss and failures in a couple of samples in our testing environment, but for 3 of the other batches, we've seen great results. So we're going to have to compare and contrast what each of these mixes had in common or different and see if we can find some results from them. And our typical testing is out to 100 days. And in Vermont, you would see somewhere between 60 to 90 freeze-thaw cycles per year. We just happen to do them every day with salt exposure, so it's harsher than you would see in the natural environment, as you're not going to be salting every day and it's not going to freeze and thaw every day. But yeah. So we'll move on away from our testing methods and previous work and talk about the Trinity parking lot. So this was the lot before redevelopment. So gravel lot, about half an acre in size, without any defined parking spaces. And so every year they had to come and regrade and add gravel to this lot, and we were told maintenance costs somewhere on the figure of $80,000 a year in upkeep of this lot. Had no stormwater infrastructure, so any rainfall, runoff, there's a large hill right here, which I'm sure most of you are aware of. This hill goes all the way down to Riverside Ave, so we see a lot of runoff and stormwater damage there, as well as inefficient parking. People have no set parking, so you'll probably see a lot fewer cars being able to park when there's no defined structure to it. So some of the issues that we're seeing, there's direct stormwater discharge down that hill from other parking and infrastructure in the front of this general campus. And so a little while ago, there was a heavy storm, and that water that was being discharged caused quite a bit of erosion and washed some trees out and had a lot of scour and damage. And as well as in the old parking lot, see large ponding areas because of poor drainage. Nobody really wants to park in that. So the proposal for the lot was to incorporate a hybrid system of pervious concrete and asphalt, and water, which fell in the center of the parking lot, would be directed out to the pervious concrete and allowed to infiltrate. For this specific lot, they went with a removable and placeable concrete section, so they come in slabs. I'll cover that a little bit later when we get into the construction. We were allowed to incorporate some research opportunities into this new parking lot, and so we thought it would be a good idea to take advantage of that. And a couple of the things we wanted to work on were to account for the total water volume that entered and left the lot, sort of like a mass balance of any rainfall, so we can come up with a number at the end of, say, a couple of years. We can look back and say, so we've had this much rain in Vermont, and this parking lot was able to reduce the runoff by this large quantity of water. And so we'll talk about each of these a little bit later, but we also wanted to monitor the effects on the groundwater table, as this lot's going to be infiltrating directly into the subsoil. We put in some monitoring wells to see if we can measure fluctuations in those soil groundwater levels. Also wanted to measure the effects on the unsaturated soil, so monitor the moisture and its temperature, as well as try and track salt as it moves from the parking lot down into the soil. see if there's a noticeable increase in the salt concentration in the soil, as that might be an issue, as well as be able to remove water samples and check for any contamination that might be present. And as well, we wanted to monitor the concrete itself, so have a measure of temperature, monitor the number of freeze-thaw cycles, as well as measure the infiltration capacity of the soil as we go, checking the infiltration. So here's a quick cross-section of the basic site design. As we saw earlier, we have asphalt in the center, which would be sloping out to the pervious concrete. Below the pervious concrete, we have a 3/8 inch stone to act as leveling surface to be able to place these pads, as well as provide some storage. Below that, we have 3-inch thick stone, which is 18 inches below the asphalt and 36 inches below the concrete. A very large storage capacity, so that any intense storm, if the infiltration didn't occur into the soil, could be stored in the system. In addition, we have some perforated storm pipes. And as you'll see, there's 4 conventional stormwater grates that allow for a backup in case the pervious concrete.
I'm just going to mute them so that you can hear the back loud.
That button.
I apologize.
It's okay. So there are 4 storm drains that would allow for a backup in case the pervious concrete was completely clogged. The water would then collect in the storm system, and pipes which run beneath the parking lot are perforated to allow any water that's collected in the storm system to then be released into the stone and infiltrated.
Sorry, so the pipe.
The pipes are connected to a discharge down the hill. Amanda, can you click on the PowerPoint? I'm no longer
Oh, I'm sorry.
control.
Try it again. You must run out of batteries.
No, that's good. Okay, so the perforated storm drains then go to a discharge point, and in the discharge, we had them construct a concrete wall that is in the middle of the concrete box. And so the water will come out of the pipe into the box, and then it has to raise to a certain level. And in that concrete wall, we placed a weir and a pressure transducer. So we would be able to measure the water level on the system side of the wall. And if high enough, it will go to the weir and begin to discharge down the hill. And so we would have a measurement of that water height, and so we would be able to tell when water would be leaving the system. As well as, so there's a roof drain that comes off of Delahanty, I believe, building, and that roof drain ties into these perforated pipe systems, and we have that similar weir inside of the concrete vault to measure any water that comes in. So by measuring the rainfall, the amount of water in off the roof drain, and the amount of water out of the system, we could do that total mass balance.
How much water have to get before it enters that perforated pipe?
The perforated pipes are connected to storm grates at the surface. The pipe isn't meant to allow water to leave the system. The pipe is so that any water collected on the surface would infiltrate into the soil. And so the water in the groundwater table would have to rise up high enough for that to then fill up, and then you'd be draining groundwater.
Were there actually had any water exit the system yet? Have there been events where?
We're monitoring that. I don't have firsthand knowledge. So this is actually the storm drains that are located at the 4 corners of the site, and this is that corner furthest away. So any water that enters there would run through the perforated pipes to this closest corner of the parking lot. So as I said, there are concrete slabs which were made off-site and delivered. Each slab has lifting locations, and so you place them down in sort of a tile section. And the idea behind these is create them in a smaller size, have much greater control over the construction and standard at which you make them, so greater compaction, allow for proper curing, rather than bringing in a concrete truck, pouring the stuff out and rolling it. And this is a new idea from a company called Suozzo Technologies, Stormcrete. And so they allow for the replacement if any of them break or clog. You can pick one out, take it away, bring in a new one, or lift it up, clean it. It's the general idea behind them. So you can see they were brought in and laid out on the two sides of the parking lot, and then asphalt was poured in the center. So this was maybe a day or two after they came and laid out the asphalt. We got our first rainstorm. So you can see that look of water on fresh asphalt and a little bit of collection here with dry concrete. So we see some good drainage from the asphalt onto the concrete and direct infiltration into the soil.
Ian, what's at the interface at the edges of each of those tiles?
In between the asphalt and the concrete, they put an expansion joint. In between each of the concrete, nothing. They just butt them up next to each other. So this was taken just this morning, I believe. So you can see the water running from the side, entering in several locations, and as the water runs in, it's going to carry some soil and stuff. It's going to begin to clog this first row, but as the water runs through, it'll eventually infiltrate in. And these were placed in such a manner that you could use less tiles on this front interface so that if you had to replace them, it would be less. They're sort of stacked in a different manner than the rest of the parking lot. Okay. That is my section.
I can,
Oh, you want me to do the whole
yeah,
thing?
sure.
Okay.
We do have a question
in between.
Yeah, go for a question.
from online, because I needed them. Can you ask on the behalf of the Institute for Sustainable Communities, what is the stone?
Sure. The immediately under the,
Yes.
can you click back on the presentation so I can go to a different slide?
Sorry.
So right there, you'll see 3/8 crushed gravel in, I believe it's 4 inches below the concrete, so that allows for a nice flat, smooth surface to lay them down evenly. And then below that, we have 3 feet of 3-inch crushed rock, so lots of void space, lots of storage capacity. And
Do you have anything between those two layers, between the 3/8 and the game?
yeah, I believe they put down filter fabric as well as fabric below the entire thing above the native soil.
More questions. Apparently, V-Trans considers gravel functionally impervious. So how is this different?
It's not gravel as in a gravel parking lot that's going to be driven over. This is a clean 3/8 inch crushed stone. So I think gravel might have been the wrong word for that. It's very uniform, has lots of void space. It's actually the same sized aggregates as we use in our concrete.
Is it washed, or is it just processed? So that there's
I think it's just the process.
All right.
Good? Okay.
I think so.
So if you had a gravel parking lot like what used to be out there, because of the constant traffic, you'd get sealing on the top, and it is functionally impervious. This would be a cleaner, more uniform stone.
Is this lot plowed like any other lot?
So they plow and salt the asphalt, and they are not supposed to plow, or they're not supposed to salt the pervious concrete. I've seen otherwise, in that I saw a large deposit of salt in the grass. It has to be plowed in order for people to park on it, and they use a special rubber-tipped plow to avoid chipping the corners and the edges, and salt is applied to the asphalt when needed for icing.
It is impossible when you're doing the salt not to spill a little bit over.
Yeah.
How it's broadcast out.
Yeah.
Yeah.
And cars track some.
Yep. Okay, so
Sorry, did they have like a special plow that they put on just for this lot, or do they use that on other lots? How much of a hassle is this for them to plow it, if they have to use a special plow? Or is that just something they use elsewhere, they don't change it?
We use the rubber chip on cups in the garage too.
Yeah. Okay. So you have a special truck that you use?
Yeah.
But this is pretty special because we are on the UAN campus that at least were able to do that and were willing to do it, but that won't be the case sometimes elsewhere. If it was the state lot, it's too much of a hassle for them just to maintain one lot.
Right. That's,
So was the rubber edge plow a recommendation of the manufacturer of the panels?
yeah,
And
I believe
guess corollary, what would happen if you just
so. If you were to
plowed
go
with a
and
normal plow?
if you were to go and buy these, they would give you some recommendations afterwards. One of them would be to use rubber tip plow. If you used the standard steel-edged plow, you would see some scraping at the top, sort of these boundary layers between the asphalt. There's going to be some small elevation change, as well as in each of these individual panels. They're not going to sit perfectly flat forever. So you would see some changes, and it depends on the plow operator. A lot of people could probably do fine and not damage it, but some are going to lift the front of their truck up and be driving on a plow in their rear wheels, and so that would cause some damage. So we've done some infiltration testing at a number of locations throughout the parking lot. Both at the interface between the asphalt and the concrete to see the worst possible clogging stages, as well as the back of the parking lot towards the grass side to see where you would expect the least secondary runoff. And so here are some of the results throughout the parking lot. For some of them, you see a general trend of reduced infiltration. There's some oddities where you have a very low infiltration and then it goes up to a much higher. That would be a sign of maybe inconsistencies in the slab itself. So if you took one of these slabs and measured every 4 inches across the whole thing, you'd be prone to see various infiltrations. We've been trying our best to cover the same space every time, but
sometimes there is a car parked.
Yep. Cars are parked there. We have to move over a little. We're mainly trying to find out if there's a trend across the parking lot. If we see every interface testing spot has severely reduced infiltration, then that would be an indication that, okay, maybe it's time to go out, check these slabs, clean them off, rotate them, do something to allow for greater infiltration at that boundary zone. And so we were given the opportunity to install some sensors to monitor the types of things that we talked about as our research opportunities. And so we have a location on the south end of the parking lot. You can see Delahanty's right here. The Colchester Avenue runs on this side. Here's the access driveway, and then you would turn into the lot. You have the Burlington School District with the children's yard. And so we have a location in the middle of the parking lot here in the south, the same sort of setup here in the north, and then we installed some sensors out in a grass section as sort of a control, because one of the ideas is we want to see if we're infiltrating water through the concrete, affecting the groundwater table, is it going to mimic the same sort of process as a grass field would? In addition, there is a water well located, a groundwater well that I installed underneath the asphalt, but I haven't had the opportunity to go and cut a hole in the asphalt yet. I'm a little hesitant because I don't want to ruin the brand new parking lot. And then we have the roof drain that comes off of Delahanty and is monitored to measure any water that comes in, and the outfall of the stormwater system that is underneath this parking lot will be on the north side. And so here's a typical cross-section of these north and south locations. We have a groundwater well installed down several feet below the water table, and in that we have a pressure transducer. So that's going to tell us the height of water above it, and we'll monitor fluctuations in the groundwater table. We have our 5 inches of pervious concrete, below which we placed a temperature sensor. We then have 4 inches of 3/8 crushed stone, 36 inches of 3-inch crushed rock, and below that we have a temperature sensor, as well as soil moisture probes located at 3 different depths through the subbase. And additionally, we have a lysimeter, which is installed in the unsaturated portion of the subbase to allow for water collection. So here are some of those probes. This is our pressure transducer, goes in the groundwater wells and measures the amount of water above to measure fluctuations in the groundwater table. These are the soil moisture probes, which are located at 3 intervals. They measure the temperature and electrical conductivity for salt content, and the main purpose is to measure the soil moisture. The suction lysimeter has a porous steel tip and allows for water to be collected inside of this cylinder, and then by using changes in pressure and vacuum, you can withdraw that water up to the surface. So place a suction on the lysimeter, and it's going to collect water over time, and then you'll be able to come and either use a vacuum to pull that water out or press air down and the water comes out one of the tubes. And so we have them installed in the unsaturated zone. So if we create a negative pressure inside the lysimeter, it will draw any available water into the lysimeter to sample the unsaturated zone. In addition, in the grass portion, we installed a rain gauge, temperature sensor. There's also a suction lysimeter and 1 soil moisture probe embedded at an equivalent distance to under the pervious concrete. And so our first slide will show the 5 available temperatures throughout the pervious concrete, as well as the ambient air temperature that was monitored over by the rain gauge. And so see the ambient air temperature measured throughout the year, and we see a pretty good correlation with the temperature directly below the pervious concrete. And so if we want to know how many freeze-thaw cycles the pervious concrete has experienced in the future or in some other lot, we can see here that it's going to be pretty close to the ambient air temperature. So one of the theories for pervious concrete that someone else suggested a while ago is that the temperature of the ground will keep the pervious concrete from freezing. And so I think pretty clearly we see that that's not the case, and we have to be concerned about the concrete freezing. Someone had suggested we're not going to see freeze-thaw cycles. It will be kept warm by the moisture in the soils and the subbase. So we obviously see that's not the case. And we have measures of the ground temperature from the deepest and what we consider the groundwater temperature, and higher as we get up in the soil profile. We have a volumetric, so we have the rainfall collection on the site. We saw a very large storm, see an increase in the volumetric water content in the soil moisture probes. And the black line is our deepest soil moisture probe, which we believe has the groundwater table has risen up, and so that's a measure of the volumetric water content of a fully saturated soil. So we see a good spike in the increase in soil that goes along with this very large storm. So we have some measure of direct increase because of a large infiltration. And so a measure of electrical conductivity at the site from that same sensor that we saw an increase in volumetric water content, we see an increase in the electrical conductivity, which will be used to correlate to the salinity of the solution. So with an increase in electrical conductivity, we know that there's an increase in the salt concentration in the soil.
We so far have data only for about 6 months, right? So hopefully we'll
Yep.
see it for the next 2-3 years.
And even though we see it fluctuating, it's still in the range of natural soil. It's not anything to do with soil. The natural soil, typically like coarse soil, will have electrical conductivity of 0.01 millisiemens per second to millisiemens per centimeter, right? That's the conductivity unit of electrical conductivity. But 0.01 to 1, that's the range. So it's all noise probably. I don't see it's due to any salt concentration or anything. So probably, I mean, they're doing a good job of not letting the salt into the pervious concrete now. Or maybe it's
Or it's not detectable.
just not detectable to those. It has not reached those probes where they're embedded.
But even if they saw the asphalt, all of that's running off into the pervious concrete,
Yeah.
and so that should show up, you know.
Yeah.
So we've been monitoring the groundwater level at 3 locations in the pervious concrete, and hopefully soon we'll have that 4th location. And so we see, again, with that large rainstorm, increase in the groundwater level, so we know we have direct infiltration, and see a pretty good control here between the west, which is in the grass field, and the north, which is sort of in line as far as the slope of the hill goes. And so the difference between the north and the south is likely due to the elevation of the groundwater table. As we go from south to north, there's going to be a change in the groundwater elevation because we have a large hill here, so water's obviously going to be lower there. But it's promising to see that the grass lot, which is in green, and the pervious concrete have the same amount of groundwater fluctuation, so we can hope that that is because we're infiltrating water through the pervious concrete and rather than discharge. So when we install that 4th groundwater sensor, we'll be able to see if there's any change between the groundwater below and impervious surface compared to pervious concrete and natural soil. And one of the undergraduate classes used some of the water samples collected from the groundwater wells to test for the pH, the presence of metals, turbidity, conductivity, and phosphorus content. And so one of the ideas when we were putting in these sampling wells is to incorporate it into some testing for courses and give a site on campus where some of those classes can go and have easy access to some subsurface testing. And unfortunately, they didn't have access to the suction lysimeters, so they were using groundwater only. But it was a good opportunity to include something on campus in their course study.
It didn't rain when the course was going on.
And that particular day, otherwise there would be car parked on the spot and all those things.
So we forgot one very important slide. is to thank the sponsors. BTANS, TRC, and so have all the instrumentation was paid by, most of it was paid by as a part of the project actually, and then TRC, and we greatly appreciate the financial support as usual, and welcome more.
So are there any questions? You can go back and
I just have a couple. One is, do you have any cost data? If you were going to pave the parking lot, you might have gone with 18 inches of gravel and asphalt. You had some additional gravel and the concrete panels. I'm wondering, if you looked at what the differential cost was, and then kind of extrapolating from that, if you were going to put in a conventional stormwater system, what would the cost of that have been? How does it compare cost-wise?
I don't have those specific cost values. I know that in previous work, putting in a pervious concrete parking lot does increase your construction and material costs. The benefit of putting in the pervious concrete lot would mean you wouldn't have to put in that stormwater system. In this case, they did put in a stormwater system as backup. I think there were some constraints as far as what sort of lot they were allowed to place here. One of the things that I had heard, and I don't know if this is true or not, is that they didn't have additional capacity in the stormwater system in this side of campus, so they needed a better best management practice type of lot to allow for infiltration. So I think there wasn't.
Luz, do you have something to add to it? You might know the story better than we do about the 385.
Well, we've always wanted to try a pervious concrete lot, and this is the perfect subsurface soil. It's very sandy on this side of campus, as close to the glacial till on the other side of campus. So that's why we were aiming to do this, and had a lot of erosion problems with the hillside. But you can see our outlet for the parking lot looks great compared to the outlet from the school district parking lot, which is the big hole with the pipes held by rope that need to get repaired soon.
Yeah.
So that was the major, it's not actually parking lot construction, it's related to the outfall.
Do you recall what were the costs?
I don't, but I could probably get some information on that. I just don't remember what the differential was.
Was there any specialized contractor expertise required? Or,
I don't believe so.
No, but
The panels were bought and delivered, and I think they had a pretty easy time of lifting them up with the small backhoe or something and placing them in.
I think the tough part was the grading because you're looking at slabs. So when the engineer and site engineer graded it, they didn't think about, you can't bend these slabs. You've got to really think about the dimensions of your slabs when you do your grading.
Yeah, so
On these kind of
straight line
projects, you're
grades.
limited. And then they had a little bit of a hard time. It's tough to get a slab perfectly level. So they struggled with it quite a bit.
Can't have any grade breaks on
Right.
this guy.
Right, you've got a 4x8 slab.
So having,
It's got to be a straight line grading.
Yeah.
having a good contractor with good field quality
Yes.
control is kind of critical.
Critical.
Related to operational costs, do you have anything to say for recommended maintenance measures and intervals?
So I don't know specifically, as my work was mainly for the laboratory freeze thaw. I know that the manufacturer of these slabs, who also owns the business of coming and cleaning them, would probably recommend yearly maintenance. We're going with monitoring the infiltration capacity, and at some point, if it needs to be addressed, you would have a suction vacuum truck come over. Typically on a yearly or 2-year basis to maintain the infiltration capacity. And that would change based on the number of trees around it, which are going to drop leaves and cause clogging, as well as the general performance of the lot.
Do you guys sand your lots at all?
A little bit, not much. It's mostly soil.
You mentioned that you had a kind of an effluent box to measure flow from the site. You had some pretty good rainfall events.
Yep.
I'm just wondering if the system was able to retain in the gravel layer and infiltrate those storms that you've had so far, or whether you actually had, or you exceeded the capacity of the system and had discharge?
We didn't have access to those to that data right now. From my experience, I've driven over here when I know it's going to have a pretty heavy rain, and there wasn't storm water making it to that last vault and then exiting the site. I don't know if that's still the case with some of these heavy rains we've gotten, but from what if you actually go out there and look now, it's a sealed concrete vault with an input pipe that's higher than the output pipe, and the concrete wall divides the box in two. And on the outflow side, the water is still not up to that outflow pipe, so there's water in there, but it's still below, so that might have been the rain that collected from falling directly on top of it, or some water making it over.
So that's one of the interesting design considerations, how much storage capacity you have in there.
And
we had record rain in May and June. It would be interesting to correlate the rainfall with, is it holding it all and infiltrating it, which would be great.
Yep, that's one of the things we need to, go get the data from the field instruments. I don't think we had time to collect that one. It seems to be a very popular parking spot, so it's a little difficult to get the results. We have really good sand beneath the system with very high infiltration capacity. So if I had to say personally, I think we've been able to infiltrate all of the storms, but the data will show that eventually. Yeah.
I understand there's some liquids that can be applied in lieu of salt. It's something along the lines of what's used in a de-isoplane or something. There are some spray liquids that do.
That's what we use. It's a magic salt that you mix in.
It's supposed to have less effect on the configuration of the concrete.
Yeah.
That's what we use now. But it's still salt. It's better.
I'm not sure on what magic salt is in particular, but some of the products include alcohol to really lower the freezing point. And there's been some studies done on the various types of salts that are available. So sodiums, calcium chloride, magnesium, I think, is what's in that specific salt. So I don't know in particular, but I tested with sodium chloride, which is the most damaging of the most commonly used salt. I think calcium chloride is a little more damaging, as it has twice the amount of chloride per salt ion. So the tests that I ran were for the salt the state uses in their lots, and we saw the most damage. So.
We've been involved in an engineering company, Engineering Ventures. We were involved in a couple of projects, including the College Street project, which I understand has some surface degradation at this point. Do you think that's the case?
From what I've seen on that lot, there was some soil carried in on a lot of car traffic, and that has a active collection system, so the asphalt runs onto the concrete, like in this lot. And I've seen much higher clogging and reduction in infiltration capacity, which would increase the saturation of that top layer, because the soil clogged in there is going to remain saturated through that freezing and thawing. So I like to say that anything that increases the saturation of the pervious concrete will result in damage. So clogging, the presence of salt, if there's not proper drainage below the system, if you didn't include enough storage capacity, so some of those things.
Another local project at Shemlin College.
Yep.
When Perry Hall was renovated and a new addition.
Yeah, I saw they put that in there.
Kind of the pedestrian walkway, going in, which was pervious concrete, and really only made it about a year until the surface began to look like gravel and was pretty much fully clogged, and has been since removed.
When was the construction on that?
Just a couple of years ago.
I mean, do you know which month of the year?
I don't know offhand.
Okay, so one of the big issues, and it's studied elsewhere, is the construction practice in the field and how much curing the actual concrete in the field gets. So in the lab, we make them in small cylinders, place them in controlled fog environment, and they're, really getting the treatment fully cured. In the field, they'll lay it down, cover it with a tarp for 7 days, pull the tarp off, and let people drive on it, and salt it in the first year. So those sort of differences are what some people are trying to quantify and what the end of our current freeze-thaw study is going to work on. We're going to create some slabs, cure them as though they were cured as cylinders in the lab, and make another slab, put it outside, see how a field parking lot would fare. The slabs that we have were made in forms, placed in a warehouse, and allowed to cure for several months. So it's showing to be stronger, fully cured. It's one of the differences between how we do things in the lab and the actual field environment. So we're working on quantifying that.
What we did, that was a big point of that project, was to make sure we ordered those slabs really early so they cured properly, and we didn't have that issue. But you're also not supposed to use a street sweeper. I think it's very clear about that. You're supposed to vacuum from. I believe Greg had said street sweeper will make it worse because you'll drive it into the concrete. That's what I remember him saying at one of the seminars on this.
What kind of controls do you have with the College Street as far as how they plow? Because here we can do the rubber plow and everything, but what do you have for controls, and are you taking that?
We were just given access to measure the infiltration of their lot. I think they had to treat it the same as everything else. So sort of in the study that Mark did, and he can speak to it if he wants, or I can, but College Street was treated as though it's regular asphalt and no special provisions were given. Heritage Flight out in South Burlington, no salt is applied. They use a rubber tip sweeper. I think they might have had to salt it once when there was a particularly bad ice storm, but between the two lots you see that College Street has clogged, falling apart, some surface scaling. Over at Heritage Flight you see a much cleaner, healthier surface, and you can actually notice where a car parks, there'll be 4 spots which have a little bit of surface rattling. So even the salt carried in and dripping off the car has caused damage in this parking lot that otherwise hasn't seen much salt use.
Are you familiar with the stretch of pervious pavement at Fletcher Free Library?
Yep, that was placed at the same time as the College Street. It's at the Free Library and the Archibald School.
Yeah, I forget which school has, the old North End has a small patch as well.
Yep.
Concrete or asphalt? Pervious concrete. We weren't there for the installation of either of those facilities though, so we didn't at College Street, we got to see it actually go in. At Heritage, we got to see it go in.
Okay.
At those 2 sites, we did see, the construction, what the temperature was that day, those type of things.
Do you know what happened to the one at Fletcher? Anyone?
Can't speak.
No. I've driven by it occasionally. It seems pretty clogged, and there's a lot of litter and garbage, and so I think it's getting towards functionally obsolete.
We have several bike pads by Bailey Howell that are pervious concrete. You can see them; those were cast in place, and then we just put more concrete at the greenhouse.
Yeah, these slabs.
Right. Yep. Ones on College Street and at Heritage, those were either poured in place.
Those were both poured in place.
Okay.
As well as the Randolph Park and Rad.
This is the only one in Vermont to date that's removable slabs.
Okay.
Yep.
So is this something that would last 10 or 15 or 20 years once you install it if you did it right? Or is that more likely to last 5 or 6 years? If it's getting regular traffic, there's no parking lot, so you get traffic that doesn't pick up stuff on its drive to work. I'm asking partly because it looks like a pretty expensive enterprise. And if they last 20 years, it might be worth it if they're going to clog like the one at the library.
So with proper construction, and if you allow it to cure properly, and we get a field site that is performing the same way that we can make them in a lab, we can make a robust enough concrete that it should last if you try to limit clogging and salt use. So you could see 30, 50 years. I mean, there's parking lots throughout the country which aren't in the Northeast, which have lasted, I think we have one going on 45 years. So it's not that the concrete itself can't sustain a 50-year lifespan. It's that our environment is limiting it as of yet. So we're working on building a robust cement paste to reduce the salt damage and perfecting some of the construction techniques for going with something like this, a removable, placeable lot.
Do you know how much the whole thing cost?
Nope.
No?
She does.
I'll shoot my numbers to you. I want to be accurate. So.
Yeah.
Can you go back to your temperature slide real quick? I just wanted to look at it.
Sure.
Question.
And in addition, we'll put the temperature from this groundwater, but I would say it would be where that black line is as well.
So I do find it interesting that even though you had a very clean gravel underneath the pavement, which would, I guess, tend to promote the movement of the freeze front, that you still remain above freezing at the bottom of the gravel.
Yep, that red one is placed, directly below filter fabric on top of that. So I think we're seeing some heat from the ground surface, maintaining that temperature closer to the groundwater. But there is also, some significant lag. You see a really low temperature here, but that decrease in the ground temperature doesn't occur for some time.
It remains frozen for a longer time instead of going through a number of cycles of freeze and thaw. I don't know which one would be more damaging. I would guess more and more freeze thaw cycles would be more damaging rather than.
I admit that the frost depth didn't reach the bottom of the gravel. The gravel stayed above freezing, which means that you don't, things like frost heave become not an issue then.
Yeah.
So.
Because we have really good draining soils, and so if you had saturated soils at that interface there or any water present for a long period of time, you'd see some decreases in temperature and frost action. So one of the sort of ideas is that we'll then count the number of freeze-thaw cycles as this goes, and be able to quantify how many freeze-thaw cycles we had. And then at some point, if they allow us, remove some cores from the concrete and do some testing, compressive strength, durability, things like that.
Well, if there's no more questions, I'll wrap it up. We have another, thank you very much, by the way, to Dr. Dewookar and his crew.